In this section, we'll talk about equations, specifically describing relationships in data. So, first off, what we call a mathematical model. These are the types of things that makes mathematics meaningful in the real world, and that the mathematical models often give an equation to describe something that actually happens in the real world. And so, a linear model is a type of model that we'll use for many different types of problems, but specifically it has the form of y equals a plus bx. You may have heard about the form y equals mx plus b, and this really is the same thing. We're just putting it in a way to emphasize how it's used. So, in a linear model, we've got an initial value a, and b is a constant amount of change that happens to y as x goes up one at a time. So, let's jump right into an example with this. We've got the cost of a furniture maker to make X chairs. So let's see if we can find a linear model for this data. So, when X is 0, C is 120. And so I think an appropriate way to do this one would be to do a little jump in our graph. And let's go by 125 at a time. So I'm going to say 100, 125, 150, 175, and 200. So, at 0, we're looking at $120 to make this many chairs. At 1, we're looking at $134, which is somewhere around here. At 2, we're looking at $148. At 3, we're looking at $162. And at 4, we're looking at $176. And so the graph of this data is simply to draw the straight line that passes through all 5 points. So that is the straight line that represents this data. So how about writing a linear model? Well, this isn't too difficult either. We're going to use c in the place of y. And then we've got 120 is my initial value. It's my initial cost, if you will. And then we just simply need to notice that this number is going up by 14, then by another 14, and by another 14, and by another 14. It appears that the costs are changing by $14 per chair. This would represent the cost to make each chair. And this is our equation to model the costs for making all of these chairs. Next, let's talk about first differences. So if we're talking about a set of data that is evenly spaced, like what we did in the previous example, then the first differences are simply looking at how this value is changing. If all of these first differences are the same, then we can talk about a linear model. So let's look right at it at this example here. So we're looking at the temperature of air at various elevations, and let's take a look at these first differences. So the way that we do these things is we simply look at what's the change here. Well, it went down by 10 to get from 20 to 10, and then it went down by 10 again to get from 10 to 0, and then 0 to negative 10 is again going down by 10, and negative 10 to negative 20 also. So this is a linear model because of these first differences. Let's write that down. Since the first differences are all negative 10, the model is linear. So now let's just find a graph for this, and let's also write down the model. So using the same rule that we did a moment ago, we've got temperature, which I'll call T. The starting temperature was 20, and then the differences were 10, and the elevation we'll just call X. So there's our model for this, and then let's plot these points that we were given. So I'm going to go by 5s for this example, and we'll go by 1s on our usual scale. So we have 0, 20, 1, 10, 2, 0, 3, negative 10, and 4, negative 20. And so we can draw the line that passes through these points, and that is our linear model. You'll notice that the temperature continues to drop as the elevation rises, which does seem to make sense in general. Next, One of the nice things about linear models and models in general is that we can use them to predict future values. So we like to be able to determine values that we don't know before we actually go out there and measure it. This is a great example of when this really needed to be done. So we have a scuba diver that takes pressure readings at various depths in the ocean. And so what we notice is that there's sort of a consistent change here as we go deeper. And so this model was used in 1934 to try to figure out just how much pressure would be on a vessel that goes underneath the ocean to 3,000 feet deep. And so this is a fascinating article to read on your own if you want, but let's see if we can figure out just how much the pressure would be at 3,000 feet. So, first off, this is definitely a linear model, and let's show why. This is going up by 4.5, and again goes up by 4.5, and 4.5, and 4.5. Every single time it goes up by 4.5. So let's write our model. Let's call the pressure P, and we'll let our depth be x. And so the pressure starts at 14.7, but it goes up 4.5 for every jump in 10 feet. So let's be a little bit careful here. Really, we're looking at 4.5 divided by 10 times x. And let me just simplify that to 14.7 plus 0.45 times x. And so now we're going to look at 3,000 feet. So the pressure at 3,000 would be 14.7 plus 0.45 times 3,000 feet. And let's see what we get out of this. I get 1,364.7 pounds per square inch. That's a lot of pressure. And so this is what had to be overcome in order to do a deep sea search.